Hello everyone, this is Ruai PCB, your trusted PCB partner. Today, our topic is the design of power and ground planes in four-layer PCBs, focusing on power planes and ripple suppression. Welcome back to the four-layer PCB power and ground plane design course. In the last session, we discussed the impact of current density on plane layer design. Today, we will take a deeper look at another important function of the power plane, ripple suppression. We will focus on how power supply ripple is generated, how the power plane in a four-layer board can effectively reduce it, and reinforce our understanding with a case study of a DC-DC converter power supply. For the four-layer board structure, let's first look at the stack-up. Signal, GND as a plane, power as another plane, and then signal again. This forms a four-layer stack-up structure. Generation and hazards of power supply ripple. What is power supply ripple? An ideal DC power supply should output a flat voltage, but in reality, due to load changes, the operation of power converters, and the presence of parasitic parameters, some periodic or random voltage fluctuations are superimposed on the power line. These fluctuations are what we call power supply ripple, especially in DC-DC switching power supplies. Due to the high frequency switching characteristics, ripple is inherent. Take a look. This is the output of a switching power supply. At different voltages, whether it's 12V, 5V, or 3.3V, ideally it should be a straight, very fine line. But in reality, we can see various fluctuations. For example, at the bottom, the 12V line shows regular patterns, while the 5V and 3.3V lines are much denser and more irregular. This is what we call power supply ripple. What are the hazards of power supply ripple? First, it affects the normal operation of ICs. Sensitive analog circuits or high-speed input circuit ICs are very sensitive to power supply noise. Excessive ripple can lead to degraded performance or even malfunction. Second, it deteriorates signal integrity. Power supply ripple can couple onto signal lines as noise, reducing the signal-to-noise ratio. Third, there's EMI noise. Ripple itself is a source of noise and can radiate through the power network, worsening EMI issues. If the power supply ripple is too large, it can easily cause the chip to stop functioning. Since there is such noise on the power supply, the same kind of noise will also appear on the signal, reducing the signal-to-noise ratio. So how can we use the power plane to reduce ripple? This is the planar capacitance effect. In a four-layer board, the power plane and ground plane are powerful tools for suppressing ripple. So what is the planar capacitance effect? When a power plane, here our layer 3, L3, is placed right next to a ground plane, which is layer 2, L2. As we can see here, a large planar capacitance is formed between them. Although the capacitance value is not as high as that of a discrete capacitor, it has an extremely low equivalent series inductance, ESL, and equivalent series resistance, ESR. This means it provides excellent filtering for high frequency noise. So how do we suppress ripple? First is high frequency decoupling. When an IC requires a sudden large current or generates high frequency noise, the planar capacitance can quickly charge and discharge, absorbing or supplying this high frequency energy. This confines the power ripple within the plane itself and prevents it from spreading. Next, it provides a low impedance path. The low impedance path offered by the power and ground planes increases the robustness of the power network. So even with large current fluctuations, the voltage remains relatively stable. It also works in conjunction with decoupling capacitors. Plane capacitance provides wide area broadband decoupling, while the discrete decoupling capacitors we mentioned earlier offer localized decoupling for specific frequency bands. Working together, they help deliver a stable power supply. Design strategies for power and ground planes of DC-DC converters on four-layer PCBs. DC-DC switching converters are typical sources of noise, so special attention must be paid to the design of power and ground planes. Here we have a direct current to direct current power supply. Since it meticulously regulates voltage through a process of rapid switching, it inherently acts as a significant source of electrical noise. First, it's important to isolate the noise source. DC-DC converters, especially buck or boost converters with switching characteristics, have switching nodes and high frequency current loops that are the main sources of noise. In PCB layout, these should be placed in relatively isolated areas of the board, away from sensitive analog sections and high-speed input circuits as much as possible. In this case, our entire setup is a power supply chain, so there isn't really a specific place to put it. To put it simply, if it's just a part of the circuit, we usually concentrate it in one area. Next, optimize the high frequency current loop. The key high frequency loops in DC-DC circuits, such as those formed by the input capacitor, switching transistor, inductor, and output capacitor, should have the smallest possible area, especially on a four-layer board. This means that the connections between these components should be tight, using short and wide traces or vias to connect to the corresponding power and ground planes. This is evident now. Inductors, capacitors, and similar components are all connected to the ground or power planes through nearby vias, keeping their paths as short as possible. Dedicated ground connections, for example, the ground pin of the DC-DC converter and the ground pins of the input and output capacitors, should be directly connected to a continuous ground plane. I might use a separate isolated group to keep the DC-DC ground plane isolated from the digital capacitor ground plane, connecting them at only one point to prevent DC-DC noise from spreading through the ground plane. Here, through the isolated group, you can see that many connections are made to ground as quickly as possible. And as we've discussed before, single point connection means that both power and ground should be connected at a single point, avoiding the formation of loops. Next, output ripple suppression. The output port of the DC-DC converter also requires appropriate output filter capacitors, and these capacitors should be closely connected to the power and ground planes to further suppress output ripple. This is straightforward. For example, the large and small capacitors on the right are all used for output ripple suppression. Different sizes of capacitors are used in power design to filter different frequency ranges accordingly. Here you can see three types: aluminum electrolytic capacitors, then the larger ones, those with a bigger physical size, are generally higher capacity capacitors. And then there are also smaller ones, which are low capacity capacitors. Today, we learned about the hazards of power supply ripple, as well as how the power plane of a four-layer PCB can effectively suppress ripple through the plane capacitance effect. We also discussed power and ground plane design strategies for DC-DC converters on four-layer boards. By understanding and applying these principles, you will be able to design stable, high-performance four-layer PCBs with excellent noise suppression. I hope this content has been helpful to you. If you enjoyed this video, please subscribe to my channel for more videos. Thank you, everyone.